because the fraction is 1. So W gamma S by gamma B is C max. So this C max, which is now in molecular terms, you can always convert mass yield, weight, and the okay. Similarly, you can do the same thing for product formation. So if you want to find the value of F max, which was the stoichiometric coefficient modulating the product, so F max was just W times gamma S by J times gamma P. And so that's the maximum possible product yield in the absence of biomass synthesis, right? So that's the upper limit that you would have. So it sort of tells us that even these very simple unstructured models do give us some predictive, or at least they give us thermodynamical maximum yield corresponding to the fraction when you put the fraction of available electrons transferred equal to 1. So it may not be always very realistic, but that's really the maximum yields of YXS max that you can get in any aerobic system. Okay, so I think we have spent enough time on all these simple stoichiometric equations now, but I left you with another question on the last part on the energy balance with chemical reactions. You all know heats of formation, you know how to find heat of reaction. So if I have A times A plus B times B going to C times C plus D times D, then you know that the heat of reaction at naught, that is subscript naught, superscript naught, that is at 298 Kelvin in 1 atmosphere standard state, is nothing but the stoichiometric coefficient times the heat of formation, products minus reactant, sigma over everything, right? So you would take small c into the heat of formation of capital C species plus small d into heat of formation of at the standard conditions of 298 Kelvin and 1 atmosphere of D minus A times heat of formation of capital A species minus B times heat of formation of capital B, right? That would give you the heat of the reaction at standard conditions of 1 atmosphere and 298 Kelvin. So if everything was carried on at 298 Kelvin, let us say all the reactants and products were also at 298 Kelvin, then you could easily add the sensible heat also, right? Because the sensible heat was just integral Cp dt and multiplied by the n moles and whatever is reacting. Of course, you have to do the material balance, find what is reacting. And if you multiply the number of moles by and integrate with Cp dt, you will have the sensible heat change. But let us say that the reference was 298 and the temperature was 298, those should always be 0. So if the reaction was carried out at 298 Kelvin, all the sensible heat changes will cancel out. You only have the heat of the reaction. But the thing is, the reactions, at least the chemical system and all the water gas and all the methane, combustion, etc., they are all at elevated temperatures. So I asked you, what should we do if the reaction is being carried out at elevated temperatures? And both reactants and products are not at 298 Kelvin, 25 degrees Celsius. The pressure part we could take care of because we said it's an ideal gas state as the reference. So there were no dependence on pressure or very negligible dependence on pressure. So that was, so even though we are not making the ideal gas assumption, there are real gases, we said that in the limit of low pressures, we can make that approximation. And that's a pretty good approximation actually for every system. However, temperature we have to worry about. And so what is the effect of the temperature then on this our balance? That's the other important question I left you with. So you need to really think on this carefully, because now today and tomorrow, and I have to also supply you some data sheets so that your integral Cp dt calculations become simpler. Of course, if you have to integrate it, you'll have to take alpha, beta, gamma coefficients like I showed you in the shared equations, shared things on Monday. You'll have to integrate it, but there is a simpler mnemonic device where you can have a mean CP, which would be a different value at every temperature above 298 Kelvin. So if I could have a graph of that, of course I can't give you all the CPDT for alpha beta coefficients or every substance, that would go into volumes. That's something you have to find in the books, but at least the mean CP graphs can be condensed in a couple pages. So I just have to find it, and tomorrow I'll share that with you. So that will be the last part, and you can also solve some questions first based on the integral CPDT and device of the linear CP, which is in some way a pooled CP mean for that elevated temperature with respect to 25 degrees as reference. So the question, so what I suggested was that you should devise a path, because enthalpy is not a path function. You should devise a path such that the enthalpy change of any reaction, first the reactants which are there, in the sensible heat change of the reactants, then the reaction itself at that temperature, and then the products at that final temperature, the sensible heat change, so that all these three effects are taken care of, and yet you can use the standard heats of formation data at 298 Kelvin. So how do we do this? This was my big question. So the answer to that is that you have to, of course, the data of the standard heats of formation, standard heat of reaction, because of that standard term and the not superscript that you have, it's only at 1 atmosphere and 298 Kelvin. So you can't, there's no value of these heats of reaction at any other temperature. So what you need to do is, suppose you could cool the reactants from the initial temperature at which the reactants at this reaction is taking place, or at which the reactants are fed. If you could cool that to 25 degrees Celsius, then you can calculate very easily the sensible heat change NCP/dt, right? Integral n integral Cp naught dt, right? From and then the required enthalpy change would be sigma over all the reactants, n integral T to 298 Kelvin, Cp naught dt, right? Because you're cooling everything from the standard states in their, you are cooling the reactants in their standard states from a temperature T to 298 Kelvin, right? And it's at a pressure of 1 atmosphere. That is fine. So the total enthalpy change for this step can be easily calculated if the heat capacities of the reactants are known. So the delta H naught of the reactants would just be sigma over all reactants, then n into integral going from temperature T initial to 298 Kelvin, Cp naught dt. Cp naught you know as a polynomial, right? So that will represent the enthalpy change of all the reactants in their standard states during this cooling process. Now, if you allow the reaction to proceed isothermally at 298 Kelvin to yield the reaction products also in their standard states at 298 Kelvin, then that enthalpy change is nothing but the known standard heat of the reaction, Celsius, right? Or delta H naught 298. That you just know how to find that, because I just showed you that you can use the heats of formation, and you would have the enthalpy change delta H naught to 98. Now we can do the same thing. Let us share the slide. We can do the same thing with the products, right? That is, we can heat the products now from 298 Kelvin Let's see where you can heat the products from 298 Kelvin to the final temperature T final. So in other words, such as let us find it. So you will have a diagram such as given here. That is, the first arrow shows all the different reactants which flow in at a temperature T initial. You cool the reactant. The enthalpy change was just sigma of NCP dt over all the reactants. So that's delta H naught R. Then carry out the reaction at 298 Kelvin. And the enthalpy change is the standard heat of reaction at 298 Kelvin. Okay, delta H naught 298. So that's fine. Now I said you can heat the products to the final temperature. So if you heat these products, you would have for every product, you would have NCP naught for that product dt from 298 to T. That would be the sensible heat change. And if I sigma over all the products, so that is sigma over the products N integral 298 to final temperature T final in Cp dt, and I integrate that and sum them. That will give me the enthalpy change delta H naught products. So this dashed line is the enthalpy change from T initial to T final, even if though the reaction was not carried out at 298 Kelvin. That's the total delta H change. And what we said is if it is a constant pressure process or a flow process, almost equal to delta H, because you're just neglecting the shaft work and the Ke and P potential energies and kinetic energies, which are generally negligible compared to all these heats of reaction and these enthalpy changes that you're calculated, because they would be 99% very often of the entire heat change, heat effect. So by the thing that this is the same, whatever be the path, this delta H is the same. Instead of going by the dashed line, which is what the reaction follows, we have devised an alternative path where we get the same enthalpy change. First, by cooling the reactants to 298 Kelvin, then carrying it out the reaction at 298 Kelvin, and therefore knowing the standard heat of reaction at that temperature. And then we heat all the products to the final temperature of the reaction. And then if we sigma all of this, we add the total delta H is also given by delta H naught R plus delta H naught 298 plus delta H naught P, and that's the delta H of the reaction. Okay, and the Cp itself, if you have to,
so just a second, I'm sharing any slides.
You can't see the slide?
No, sir.
Oh, I share. I share, but let us go through it again. Now, is it visible?
No, sir.
No, sir.
Okay, 1 minute. Now,
No, sir.
well, let's see why it's not. Okay, let's see. Is it visible now?
No, sir.
Why is that?
Yes, it's visible.
I don't know why I just did the same thing. So let me then go through this very general procedure which you will repeatedly use. Okay, we were just it just went off for some unknown reason. Is it now? You can hear me, and let us see if you can see the slide. Okay, is it available now? We were just logged off. I don't know what happened. Doesn't look.
So the screen is not visible.
Well, I don't know what happens. Uh, I don't know. We just got logged off. So anyway, it's there, but according to it, say, even though I say share it, it's not doing it. I don't know why. What the problem is? No problem. We will again try it tomorrow, but it's there in your textbook. It's there in every, whether Himal Blau or Felder. Basically, what you do is cool all the reactants to 298 Kelvin from a temperature. Generally, it will be higher. If the, suppose the reaction inlet of the all the gases is at 298, the enthalpy change, sensible heat change anyway is zero, right? So the integral NCP dt is zero. Okay, so that will be delta H naught R for the reactants. You have to sigma over all the reactants, right? With NCP dt for all of each one. Then carry out the reaction at 298 Kelvin. That's delta H naught 298 standard heat of reaction, which you know how to calculate from the heats of formation. Then heat the products in their standard states from 298 Kelvin to the final temperature T final. So the total enthalpy change for that final step is given by delta H naught products equal to sigma over all products n integral 298 to the final temperature T final Cp naught dt, where Cp naught is for every product. So those values are given as alpha plus beta T plus gamma T squared plus delta T cubed, what have you. So we just have to integrate it. So what I have to, however, share with you is a simple mnemonic device to not, so that you don't need to calculate that integral. That I hope gets shared tomorrow. Otherwise, this is exactly what is there in the slides. If you want, I can actually take a question down and try to solve it, and today or tomorrow we can actually do the exact thing. Take a very simple one, and then we can go to some little more complicated one. So question is, calculate the standard heat of combustion. Calculate the standard heat of combustion of methane at 500 to do this. So at 533 Kelvin, the products of combustion are of course CO2 gas and H2O gas. So now you will have to, the reactants are coming in, CH4 and oxygen are coming in at 533 Kelvin. Okay, in this case, the initial temperature and final temperature are the same, but they could be different. T initial, T final could be different. We can try that type of problem also tomorrow. So here you'll have to go like the reactants at 533 Kelvin. That is 1 mole of CH4, 2 moles of oxygen. And here we are taking all complete combustion, so the mass balance is very simple. But in general, since you know how to do incomplete combustion, limiting reactant, etc., you can also do. We can always have a problem where you have to do the mass balance. Then you will cool these reactants, so that will be delta H naught R for the reactant. So that's nothing but NCP dt from 298, or rather NCP dt from 533 Kelvin to 298. That's the enthalpy change of the reactants. Then find out from the heats of formation the standard of heat of this combustion reaction at 298, and then heat the products to 533 Kelvin. So integral NCP dt for each product, and sigma sum over all products from 298 to 533. So why don't you try this question and last time screen. Does it show up now?
No, sir.
No, sir.
There's just some problem, you know, I mean. Though I say share, it doesn't seem to do it. What I would definitely want to share tomorrow are those linear mean. I told you that, you know, instead of integrating, you can have linearized CP mean. So take down the CP mean values for these 4 components. Methane is 1 minute. What are the units for the CP? Is it in calories or is it? I think it's in calories per mole Kelvin. Okay. So take the average molar heat capacities from 298 Kelvin to 533 Kelvin. For methane, it's 10.0. I will give you the units. For oxygen, 7.3, CO2, 9.9, and H2O, 8.2. You understand? This is the CP not mean for that. That means they have already integrated everything from 298 to this temperature. Then they divide it through by the difference in temperature, 533 minus 298, and that is this. And the units here are calories. So you have to convert them to joules. So it's calories per gram mole per degree centigrade or per Kelvin. Okay. So calories per gram mole per Kelvin. That's these values. So if you just take these values and just multiply it by the difference in temperature, 533 minus 298, that will be the enthalpy change, sensible heat change for that particular reactant or product. So you don't need to integrate. So what I have to give you is a graph. I hope tomorrow I will just see if I can share it. Otherwise, I'll send it to you by mail. So that you can use these. So I think you have the complete set of data to solve this question. You have a single reaction, and I mean, I'll show you how to extend it to multiple reactions. So you have the average molar heat capacities for this temperature range of this problem. As you know, this as the temperature increases, CP naught mean for every gas will increase with temperature, right? So so this is the value for 533 Kelvin, which is what you want. Of course, reference is always 298 Kelvin. So you have the values of in calories per gram mole degrees Celsius of 10.982 for methane, oxygen, H2O respectively, and it's all stoichiometric. You don't need to worry about those. So all you have to do is just apply the equation and find out all the 3 enthalpy changes and sum them up, and that by the state function, that's the same as the delta H, as if the reaction was carried out at 533 Kelvin. I don't know why the screen doesn't share. Every day it has shared only the last. So what we have to do is let us solve this tomorrow, and I'll give you a more interesting problem. And most important, you need I mean, I just dictated you from the graph, the CP not mean, but you have to read it from the graph, right? I mean, I have a CP mean graph here in 2 pages for all these reactants. I mean, for all these gases. So, you basically the delta H. It's like you can just take n times CP naught mean minus O and sigma over the products minus n times Cp naught mean sigma over the reactants, and all of this, if you multiply by 533 minus 298 or the delta T, you will get the sensible heat change, right? So what you should just correctly read it from the graph, which I have to provide you. So just remind me, because otherwise you won't get the data. And here in 2 pages, you'll have the whole data to solve any energy balance equation. Of course, heats of formation data you have to take from other tables. I can't give you because that's a very large table. Because for everything, you will be given a heat of formation. That's a long, extensive list. So that is something you have to get from other books. So when you add all these three after multiplication and considering delta H naught 298, the answer you should get is about minus 192 kilocalories per gram mole. That's the answer you can check. And the delta H naught at 298 Kelvin also you can find. As it turns out, in this case, the sensibility change doesn't make much of a difference. It's all dominated in this particular example. But that is because it's at 533 Kelvin, not very much different. But many often when you heat the products to over 1000 degrees Celsius, then you will find that all the terms are important. The value I gave you was for delta H naught. The final delta H naught at 533, that's the answer, which is about minus 200 kilocalories per gram mole. That's the answer you should get. So see if you can get it. Otherwise, we will again discuss it tomorrow. Okay, so let us discuss this question and any other question. Basically, let's try to solve something more interesting than just a single reaction, or maybe we should try to maximize this here also, because if you put delta H equal to 0, you will get the maximum final temperature, and you could be asked to find the maximum temperature, which is the maximum flame temperature. There's so many variants you can do, and then we need to share the average heat capacity information in which I have with me, but let us see how to share it tomorrow, and that will be the energy balance with reactions. All right, let us try to wind up, and you can also discuss this group business. You can make group of 6 with 1 leader each. Okay. All right. Thank you.
Thank you, sir.
Yeah, welcome. I'm sorry, I don't know why it's not sharing, but
those are no issues.
Can't do anything about it. Okay. See you tomorrow.
Thank you, sir.
Yeah, thank you very much, Ash.